Hi, this is Caleb. I'm going to be talking about the functional programming language Haskell today. In particular, I'm going to be talking about the topic of functors, which can be a little bit challenging to some, and I'm going to be going on a little bit about how I came to understand it and get to the point where I felt comfortable with using them. Prior knowledge to this expected before you watch this video is basic computations and understanding of how lists work in Haskell, including like infinite lists and things of that sort, and zipping lists together. Functions, higher order partial application of them, curried functions, composition of functions, pattern matching, building functions, that kind of stuff. But if you got all that, and you want to learn about functors now, then this is the video for you. So as you can see, I've got GHCI, the interactive Haskell prompt over here open, and as well as the Notepad++, my text editor. I got some content in there, examples and things of the sort. And by the way of examples, all of my examples were taken from Learn You a Haskell and a post on Stack Overflow. Both of those links are in the description, so if you want to check them out for yourself, you can. But without further ado, I'll go ahead and get into it. So as you can see, the definition of a functor in Haskell is class functor f, where fmap has type a to b to f to a to f to b. So what this is saying is we have this function fmap. Here is the type definition for it. But we're not defining it yet. That's what a functor is. So it takes a function that takes type A, and results in a type B, and it takes an f of A, and then it gives you an f of B. So this f is kind of mysterious right now. Not really sure what's going on with that f, but it looks familiar. As we can see right now, f is taking as its argument A over here and B over here. So f must be a function that takes a type. Another name for this in Haskell is a type constructor. So now we need to know what f returns. So let's look at an example of a type constructor. Maybe. Okay. Data maybe takes type A and it gives you nothing or just A. And these are types. So you have the type nothing, you have type just A. So let's go ahead and see. Or these are values. I'm sorry, these are not types. These are values. But let's see the type of nothing. Nothing has type maybe A. All right, makes sense. Let's see the type of just 5. In fact, let's do it this way so it's a little cleaner to look at. Just 5. So yeah, there's just 5. Let's see the type of it. It is a maybe integer, right? Because 5 is an integer. Let's see the type of this. It's a maybe string, right? All right, so basically a type constructor takes a type and gives you back a type. A way that we can look at this at the GHCI prompt is with the kind flag, or just k. So k of maybe, for instance, tells us that maybe is a regular type to a regular type. All right. So let's see how this relates to like int or char, right? Or bool. These are all top level types, right? They're just types. They're just kind of like values. Values are just values. You know, value of 5. It's just A, where A is a num, all right? But then the value of a function would have been, you know, A to B or something, which in our case, k of maybe is a function. It takes a type and it gives you a type, all right? So that's what functor needs from us. So let's look at one implementation of fmap, which is map from the lists. So a little refresher, map of odd onto this here would be tell me which of these are odd in the list and give me a list of those values, right? So it took a list, 1, 2, 3, 4, 5, and it asked each one, are you odd? And if it was, it returned true or false, and it gave us a list of the results. Map of a section, say +2, on would result in 1 + 2, 2 + 2, 3 + 2, 4 + 2, 5 + 2, and it would give us that list. Now that's, the type of map, if you look at it, it looks very much like the type of functor. Alright, the type of fmap, sorry, type of fmap. So what is it about fmap that is similar to map? So the relationship between them is that map is a specific implementation of fmap for lists. Alright, so fmap is the generalization of that. So what do I mean by that? What else would you act on? Well, a list is a data structure, right? So say you had a tree, right? What if you wanted to apply a function to every element of that tree? You couldn't do it with map. That's where fmap comes in. Fmap says, here's a function, and here is a data structure of elements. Apply that function to everything in that data structure and give me back that data structure. So fmap is going to need to know a couple of things. It's going to need to know how to traverse that data structure in order to apply that function. So let's go ahead and take a look at a simple use of that down here. Alright, so functor and tree, right? So we're going to say tree is either empty tree or it's node with a value and then another tree and another tree, the left subtree and the right subtree. So here's how it's going to happen. Tree is a type constructor, right? Fmap is going to take a function that we don't care about because we're not going to use them, and empty tree, and it's going to return an empty tree. That's the recursive base case. If we have fmap and a function applied to a node with a value in it and a left subtree and a right subtree, we're going to return the node with the function applied to that value and the recursive fmap of the function applied to the left subtree and the function applied to the right subtree. And those will eventually reach the empty tree case, and we'll get a full tree of all of our values changed. So if we had the 1, 2, 3, 4, 5 in a binary tree, we could fmap over them with odd, and we would pass the tree, and then it would return to us a new tree filled with booleans. So wherever each element was, if that element was odd, it'll be true. If it's not, it'll be false. So all fmap is a generalization of map in order to work with all data structures. Really, fmap came first, and map was a specific use of that for lists because lists are so useful, right? So that's all that functor is. I get a lot of people talking about a box in the thing, and I did come up with a box example, but after I realized the data structure example with the tree, it wasn't really that useful. But pause the video and take a look at this if you really want to. This is just another implementation of maybe, honestly. So that's all I have for this topic. The only other thing that's really interesting about these that you can get into is working with I/O, input, output, and actions, because you can simplify some of that process and modify input from the user in one line, which is kind of cool. But it starts getting into things like monads and some fancier notation, which I think would be better put in another video. So yeah, thanks for watching, and I hope you learned a little bit more about functors and Haskell. Thank you.